My name is Steve Ashley. I'm a research associate at the University of Cambridge, and I'm going to be talking about certain aspects of the proliferation resistance relating to thorium-uranium nuclear fuel. This work is funded by the Engineering and Physical Sciences Research Council and forms one of a series of Indo-UK projects where the UK and India partner on various civil nuclear related topics. And given that we're linked in with India, thorium is of prime interest to them. So, to give an overview of what I'll be talking about, I'll be give a very brief overview of the global reserves of thorium and uranium, how the reserves are geographically different as such, and exactly which countries have particular, as I say, which this might be of particular pertinence to. I'll then give a very brief overview in terms of nuclear energy systems which can adopt thorium-based fuels, limited purely now to thorium-uranium fuels. I'll go over a few historical attempts, some technologies which can be considered in the medium term, the future technologies, and also far future technologies as well. I'll then briefly mention about proliferation of thorium-uranium fuels, basically to compare uranium-233, which is bred from such a system, its comparison to plutonium-239, and then the relative advantages and disadvantages for these fuels. Finally, I will, as this project is somewhat in its infancy, I'll give a brief overview of some open questions which I think are of particular pertinence and particular interest, and of which I welcome any feedback on. Okay, so what I show up here is the graph of the world, or a map of the world as such, and the percentages which are shown denote the reserves of uranium ore globally. For all the percentages, the current estimates given as such are 5.4 million tonnes. This does not include places, this is inclusive of places where there are moratoria on mining, but assumed to be either reasonably assured or can be somewhat speculatively inferred. Accounting for other sources of uranium, say for example from either coal ash or from phosphates, the total amount which is expected, at least on the Earth's crust, is 19.2 million tonnes. And most of the countries which are of particular importance in terms of mining the uranium stem through from Australia, Kazakhstan, and also Canada. If one looks at thorium reserves, and of which this work is now gaining much more interest, the percentages are somewhat rather different. So one sees that India is the main prime interest, also Brazil as well. The main difference is that in terms of where thorium is gathered from, most of the thorium which is available in India comes through from beach sands, with much smaller amounts being available from typical rock mining. And so, hence, typically you don't find thorium located in the same places where you find uranium. And so, at least in terms for India, given that it's such a large abundance of this material, they're trying to use that as part of their closed nuclear fuel cycle, which I'll come on to. Currently, thorium estimates are around 3.8 million tonnes. The amount which is speculated in these countries which are in purple totals 6.4 to 7.5 million tonnes. There's an interesting discrepancy, though, because one would expect that the half-life of thorium is much, much longer, so there should be an awful lot more of it actually in the ground than uranium. There should be around about 3 times as much material as that. So expect around about 60 million tonnes. The main question is that a lot of countries haven't put data out on just exactly what their reserves are. The most notable emission is probably between China and also Turkey as well. So that outlines the ore as such. So in terms of systems which are trying to use thorium-based fuels, nuclear energy systems, There are two past technologies which are of prime interest. The first one is the shipping port light water breeder reactor, which is in Pennsylvania, USA, which operated from 1977 to 1982. It's a typical light water reactor, so it had fuel pins made of blended thorium and uranium fuel. The uranium had 1%, or ranged between 1 to 5% weight of uranium-233, which was separately reprocessed at Hanford and Savannah River. And the U-233 content was 98%. This was down-blended with thorium, and this operated through successfully for 5 years. As it was a breeder reactor as well, the amount of uranium-233 which came at the end of life was actually more than what was initially put into the reactor. The second main type of technology which could use thorium, and the most pertinent case was the thorium high-temperature reactor in Germany, are gas-cooled graphite-moderated reactors. In both of these cases, these were demonstrator reactors, dogged with a number of both technical and also political issues. But for the thorium high-temperature reactor, the basis was that it was a pebble bed, so one had pebbles of thorium and uranium fuel. The uranium as well was high-enriched, 93% uranium-235. So these are existing technologies which could use thorium. As thorium is fertile, one needs to have an initial a greater yield of a fissile nucleus to start the reaction off. So typically for these systems, one needs a higher enrichment of U-235 to start at the start of the fuel cycle. In terms of the medium range as such, or let's say near future, the Advanced Heavy Water Reactor, which is currently being developed in India, forms the third stage of their three-stage fuel or closed fuel cycle. So with this reactor, they would take uranium-233, a certain amount from its fast breeder reactors, and also U-233 recycle from this reactor. The reactor contains thorium as well, and it's effectively it's a development of between the CANDU reactor and the steam-generating heavy water reactor. It's along that line of development, and these are scheduled in terms of siting within the next 3 years. In terms of developing the gas-cooled graphite moderated reactors, there's plans under the Generation 4 International Forum to develop very high temperature reactors. These would differ from existing technologies by pushing the outlet temperature to very much higher temperatures to gain greater efficiency as well. These would also work with large burn-ups, which is or long fueling times, which also favours thorium as well, as it gives it longer time to breed up uranium-233. In terms of the far future, there is work especially within the UK, also within the US and India as well, to look at accelerator-driven subcritical reactors. This as such has a core which cannot maintain criticality without excess neutrons coming from spallation reactions provided by an accelerator which feeds into the reactor. Probably the best example case of this is the Mirror reactor at Mol, which is a demonstrator reactor which is being built in Belgium, and that is a technology in terms of the accelerator operation which is needs an awful lot more work in terms of the efficiency of the accelerator in terms of downtime and so forth. The other technology which can also be considered in the far future is the molten salt reactor. This as such is a liquid fuel based reactor. Currently the designs are changing somewhat given it's so much in its infancy. The basis of this reactor is through from the molten salt reactor experiment which ran in Oak Ridge. And both of these technologies are gaining a lot of traction, at least in terms of politically. So in terms of, and also thorium as well, has been gaining much more political acclaim. especially recently with the forming of the Weinberg Foundation, non-governmental organisation, and also now very recently an all-party parliamentary group relating to thorium. So one of the main advantages, which is often touted for these systems, is that they're inherently more proliferation resistant. And this is one part which we want to cover. So although we have a system which is made up of thorium-232, we end up breeding uranium-233, which is ultimately fissile. And the question is, as such, well, if one has a fissile material, how does it act, and how does it compare to plutonium-239? Back in the early 50s, there were a series of tests involving uranium-233. So the most one of the main references for that is the military effects test of Operation Teapot, which took place in 1955. The core was listed as containing plutonium and uranium-233 and delivered a total payload of 22 kilotons. Secondly, as well, from Chuck Anson's book on US nuclear weapons, quotes there, in late February 1953, results of tests of Los Alamos Scientific Laboratory indicate that U-233 would not be a satisfactory nuclear explosive, and the Army changed its requirements to use U-235 as nuclear fuel for the 8-inch shell. And so the question is now, the real sort of question really is, well, why did the US go away from uranium-233 to going more into plutonium-239? And now, given that 50 years has passed, in terms of, say, technologies as such, would this now be much more of a pertinent issue in nowadays? Okay, so if we compare U-233 to plutonium-239, just thinking of its bare critical masses, both for Plut-239 and uranium-233, the bare critical masses are around about the same values. If one thinks of plutonium, or at least the material properties of plutonium, you can grade plutonium in various different ways. So often one may refer to weapons-grade plutonium, which is typically around 94% plutonium-239 and 6% plutonium-240. And all of these isotopes which are made within that mix have various different properties which either, well, at least for the other isotopes, make the overall mix of the plutonium less desirable. So, for example, if there's a large amount of plutonium-238, it can comprise a fairly large heat source. For plutonium-240, one has spontaneous fission through from that, so it could be a source of pre-ignition, and also Plut-240 and 242 act as poisons. The question is, for uranium isotopes, if one has a thorium-uranium system, well, we know that weapons-grade uranium is around about 94% uranium-235. We know that low-enriched uranium and non-weaponizable uranium is 20% U-235. And that for the other isotopes, you have uranium-232, which is a heat source and is highly radiotoxic, and for uranium-234, and 236, which both act as poisons. So the question is, what is the definition for weapons-grade and reactor-grade uranium once there is uranium-233 in there from such a, as I say, what you'd expect from such a thorium-uranium system? So finally, as such, to give certain indications in terms of the possible fuel cycles, one of the papers, a study of this, an early study by Kang and von Hippel, mentioned that the thorium with low enriched uranium, enriched to 20%, with a very high discharge burnup. So what's quoted there is a discharge burnup of 70 gigawatt days per ton, which is typical, which is sort of compared to 40 to 50 gigawatt days per ton for a conventional PWR. For a U-232, U-233 ratio, which is presented, if one has a 5 kilogram bare sphere of U-233, one has a rather large corresponding dose rate, and the dose actually comes from the beta decay of thallium-208 from uranium-232. So you have a series of alpha decays, and then ultimately ending up in thallium-208, which beta decays and gives a very high energy gamma ray, which is very difficult to shield. The dose rates given are 130 millisieverts per hour, raising up to 380 millisieverts per hour over time. So it's not quite self-protecting, but it's still rather nasty. Also, one desirable of this is such as that although less plutonium is made, the plutonium content is typically higher than what it is for a corresponding PWR. However, the issue comes is that in low burn-up scenarios, so say for example if you take a heavy water reactor, one may be able to have separated target and driver fuels, and by having this you can reduce the content of uranium-232, and you can probably get it down to a level in which it becomes, in which one's able to shield this. And so also, given the lack of a spontaneous fission source, U-233 could possibly be adopted in gun-type assemblies as well. So there's certain questions with regards to how it could be implemented. And so as such, the main take-home of the talk as such is the proliferation resistance of thorium fuel cycles depend very much on how they're implemented. And so the open questions. Firstly, what reasons led the US to stop pursuing 233 for weapons purposes, and what developments within the last 50 years could make U-233 a concern nowadays? Secondly, as showed before, what would the definitions for weapon grade uranium be, inclusive of uranium-232 and uranium-233? Thirdly, would you by having thorium-uranium systems, would you have additional pathways to obtaining the specific or alternative nuclear materials? Is 20% low-enriched uranium, which is although is not weaponizable, a sensible upper limit for uranium enrichment? Typically 20% has been accounted for certainly for research reactors. In a civil nuclear fuel cycle, is that still the case? And if not, what impact does this have? Also as well, given that you have a very highly enriched feed material, what would other alternative enrichment technologies, how would they impact on this? And finally, would thorium-uranium systems be more difficult to safeguard in terms of particular material accountability? So with uranium-232, for example, having such a large gamma ray emission rate, might it actually be hard to tell what uranium-233, what uranium-235 you actually have in your final feed material? Okay, and on that note, I conclude. Thank you.